Welcome back, everyone. In this video, we're going to continue talking about load balancing strategies and diving into some other alternate ways that we can expand the reliability of the systems we're building, especially at this level, connecting between load balancers and servers. So diving into this here, I've got this new component for you, which is the reverse proxy / load balancer that we were discussing in the last video. So here, if we were to put this inside of our system, we have requests that come from clients and the internet to our reverse proxy / load balancer. And then from here, we distribute them to our servers. Now we have, of course, web server 1, 2, and 3. Let's go over some of the strategies we already know. We've talked about the round robin before, where requests essentially just get evenly passed over one by one to every server in the list. So this is a very rudimentary strategy where we try and balance the load by just making sure that every time we get a request, we send it to the next server in the list. Now, the problem with doing it this way is that the servers themselves are often independent of one another, and they do not have any knowledge of the other servers. As a result, it's very easy to have some type of issues within the structure of doing round robin, because these servers oftentimes have different amounts of resources, bandwidth, etc. Just because you assume, even if the requests are the exact same and consume the amount of resourcing, the servers themselves might have a different amount of resources available to them individually. This is one of the key problems inside of doing this round robin strategy, and it's also one of the factors we have to think about with a load balancer. So I mentioned earlier that these servers do not know about each other. They don't know how many resources are on each other. This is due to the fact that, generally speaking, load balancing is designed to be simple for the actual execution in the architecture. Because the servers don't know anything about each other, they don't know when other servers go down. All they know is that when I get requests, I handle them. I don't know how many other servers are being utilized right now in order to serve requests. All I know is that when I get requests, I deal with them. I'm only focused on myself. This is fine. We just have to adapt some of our strategies and some of the potential load balancing techniques that we use. Another load balancing technique is known as weighted round robin. So here you'll notice on the left of each server, I've assigned a weight. Now, this means that the servers themselves are assigned a certain amount of weight depending on how many resources they have. The higher the number, the more resources. So here I've said that server 1 gets 3, server 2 gets 2, and server 3 gets 1. What happens now is that when we send requests, we're going to send the amount of requests equal to the weight in each run. So let's see what that looks like. So first, server 3 is going to get 3 requests, then server 2, 1, then server 3, 1. And that will be one run. Essentially, what happens is that as requests are coming in, we're just going to send 3 to server 1 first, and then we're going to send 2 to server 2, and then 1 to server 3. So then if we keep going further, you'll notice that that's what happens every time. We're going to send 3 to server 1 before we send 2 to server 2, before we send 1 to server 3. And then we're going to send the next 3 to server 1, and then to 2 to 3 again. This works as long as you're able to actually create a proper value and weight to assign to each server. We do this weighted round robin because it's a very efficient way of not overloading all the servers evenly, because generally speaking, most servers are not equal. The other advantages here is that we can easily A/B test things, because let's say server 1 has the new changes that we want to make, and we want to route all, or not all, but we want to route a majority of traffic to server 1 so that we can test and see what's happening here. Maybe server 2 has another change we have, but we don't really want to route everything there, and then server 3 has the old website. Here we can route accordingly, and then we can A/B test based on the data of the performance. So this is another good thing about weighted round robin and just this general style of breaking up the traffic unevenly based on server capacity or server need. Finally, the other one we saw before was least connections. This, of course, has to do with either sessions or, depending on how many requests are on the server, we determine that we pass requests to the one that has the least. So here, between server 1, 2, and 3, 3 right now has the least, so we're going to pass the request to server 3. And now what we notice is that when the next request comes in, it's really just server 2 that has the most connections. Between server 1 and 3, both are valid to go because they share the same number of connections. So here, we can just rely on round robin again, or even weighted round robin, we can do that too. We can mix the strategies together. For us, if we just went with round robin, we would just pass it to the next one in the chain, which is server 1. And that would be it. This is least connections. Now remember, you can combine some of these strategies together for load balancing, and then there's a few others that are not uncommonly used, but you can easily now start looking at different load balancing strategies that exist. There's honestly a lot of different algorithms for load balancing. It's one of the topics that is the most widely attempted in many different circumstances with many different algorithms, but the ones that we've covered here are the most common ones. One additional strategy has less to do with how we balance load, but also related to load balancers altogether, but more so from a system design standpoint. Here, we've looked at these load balancers as they are, but one thing I want you to notice is that there is a single load balancer here inside of our diagram. If this load balancer crashes, which it can, any component inside of the system can overload, go down, or suffer a critical failure, whatever. In this case, the entire system breaks. What we call this is a single point of failure, when you have a single component that essentially can go down and then destroy the functionality of your entire service, or at least a core functionality of your service. In this case, what we want to do is we want a redundant backup load balancer. So all this means is that this load balancer is not used. When requests are coming in, we rely on the first primary load balancer. If this load balancer gets overwhelmed and it crashes, what we can do is then swap it out for the backup load balancer, and now essentially the behavior will continue while we try and resolve the issue going on with the broken load balancer. So this redundancy allows us to reduce the single points of failure. Now again, maintaining a backup load balancer increases the cost because it's an increase in complexity, and it also adds resources that we need to spend to maintain a passive backup load balancer. But unless you're designing for a system that has very low traffic or a very limited chance that your load balancer goes down, you almost always want to have a backup load balancer just to reduce this single point of failure or eliminate it altogether. That is a very critical thing you want to look at when designing your systems. You want to be looking out for these single points of failure. If that exists, you want to increase the redundancy by adding backups. And maybe they're passive, they're not always running, but the moment anything that is critical crashes, you have this backup that will take its place immediately. So that is load balancing strategies. In the next video, we're going to talk about another different alternative strategy that can be used or often is used in conjunction with load balancing called clustering. So join me in the next video where we'll talk about that.